Welcome, everybody. It's my pleasure today to introduce Matthew Kahle, and he'll be telling us about configuration spaces of hard squares.
Thanks, Henry. Am I unmuted?
Yep.
Thanks a lot for the invitation to speak. The Applied Algebraic Topology Research Network has been going for a while now. I think it might have started around the time some of us were at IMA around 2013, 2014. So, and maybe you can't see if it's blurred. I have my IMA mug to drink my tea out of this morning in honor of the long rich history of Applied Algebraic Topology Research Network. And, I think it's been particularly valuable for our community, during these pandemic times and so on. And I think it'll be really valuable going forward to have some of these talks archived and, as some of us don't travel as much as we used to for whatever reasons. Maybe we have small children at home. So anyway, this is a really nice opportunity to get to have a seminar talk and from the comfort of my office. So yeah, please feel free to interrupt me with questions or comments. It's more important to me that people take something away from the talk than that I get through all my slides or anything like that. So as the title suggests, I'd like to talk about configuration spaces of hard squares today. I think it's fair to say that the study of complicated configuration spaces has been a mainstay of applied algebraic topology from the beginning. So, for example, Michael Farber and his collaborators, Robert Griest and his collaborators, and many others have worked on configuration spaces with the motivation of motion planning for robots. So Michael Farber has a nice book, for example, Invitation to Topological Robotics. And you can get into, for example, configuration spaces of planar linkages there, or Farber's topological complexity itself is a whole area of applied topology where there's a certain homotopy invariant that measures the complexity of developing any kind of motion planning algorithm for the topological space. So we're going to talk about configuration spaces of hard particles. Today it'll be hard squares, and I won't get into it a lot today. You'll see some discussion of it in our papers if you're interested, but we were also interested in physics motivations for the kind of configuration spaces we study. So for example, configuration space of hard disks, that's what we might call it as mathematicians, but physicists might call it the phase space or energy landscape for a hard spheres system or for a hard spheres gas. And hard sphere systems are known, or they're known to physicists that they're expected to go through phase transitions. There's something like a solid liquid phase transition, even if your atoms are just disks. And the only energy potential is the energy potential that says the disks are not allowed to overlap. In other words, the energy of the configuration is infinity if any pair of disks overlaps, and it's zero otherwise. Even in such a simple system, from computer simulations at least, it seems like there's something like a liquid solid phase transition, but nothing like that is known mathematically. So that's some motivation for the kind of things that we're going to talk about today. But just in the interest of time, I thought I would not talk too much about the physics today, just acknowledging that it's there in the background, and it's one of the things that originally got me interested and exciting to study these things. So I want to tell you about two papers today. One is from, I guess a few years ago, and it's to appear in algebraic and geometric topology. This is with, from left to right, Hannah Alpert, Yuli Bauer. I'm one of the authors, Bob MacPherson, and Kelly Spinlove. So we'll talk about homology of these spaces. So what are the spaces, first of all? So we'll use this notation consistently throughout the talk. CNPQ is the configuration space of n unit squares sliding around in a P by Q rectangle. So the sliding squares aren't allowed to rotate. They have to keep their sides parallel to the axes. So you might think of, for example, the classic 15 puzzle. Maybe you played with one of these before. The 15 puzzle is, you can slide these 15 pieces around. There's always one hole that you can move a piece into. So I usually think of the 15 puzzle in a sort of discrete way, because it's, to really move the pieces around, you have to slide a square completely from one position into the next position, and then the hole is in a new grid position, and then you can slide a new square into that new hole. But our configuration space, we think of it continuously, that it makes sense to have the squares in any in between position, and the only rule is that the squares can't overlap. So let me make this a little bit more precise. So we have 2n real coordinates because we have n squares. And so we need to record the center of each square, its position. So it's xi, yi records the center of the ith square. And then it's inside, the whole square needs to be inside this p by q rectangle. So there's really only like a width of p minus 1 available to the square, because the square has, if the center of the square is here, then there's 1/2 on each side that needs to stay in the square. So we could say xi needs to be between 1/2 and p minus 1/2 to make sure, but why not just make it integer coordinates and shift it to the right by 1/2? So that the boundary square that we have is actually what the boundary rectangle that we have is actually what has half integer coordinates. But so this seems like a little bit nicer. So yi then can be between 1 and q for the same reason. And then we also need that the squares are not allowed to overlap. At least they need to have disjoint interiors so that they can touch at the boundary, but they're that's all. So then, oops, that's a typo. That should be xi minus xj, yi minus yj. The max needs to be at least 1. So in other words, in the L infinity norm, the distance between the square centers is at least 1. So that last condition, that inequality, just assures that the squares don't overlap. They're allowed to touch at their boundaries. So this is the whole sort of philosophy of configuration space, is you can keep track of all possible coordinates for a complicated system by just thinking of one perhaps manifold or complicated shape in a much higher dimensional space. So rather than thinking of in ordered pairs, we just think of one tuple and 2n dimensional space as the essential idea. So another point to make that sometimes I spend more time on, but I won't talk much about today, is that I'll just write that CNPQ is a subspace of CN, which I might use for notation. This is just the configuration space of endpoints in the plane. This is the subspace, right? So the configuration space of endpoints in the plane is just x1, y1 up to xn, yn. Those just have to be real numbers. And the only condition is that xi, yi is not equal to xj, yj whenever I is different from j. So this is the complement of a complex hyperplane arrangement. It comes up in many, many different areas of mathematics, the configuration space of points, and it's very well understood topologically. So for example, Vladimir Arnold in the late 1960s he computed what is the homology of this configuration space, even the cohomology. So yeah, one other comment for those of you who are familiar with configuration spaces, to be precise, now and throughout the talk today, we're always talking about ordered configuration space. So that's just as we've defined it. So you can tell the difference between particle 1 and particle 2 and particle 3. They each have their own coordinates, but sometimes people like to look at unordered configuration space for many reasons. And that's just the quotient of this space by the natural SN action. The symmetric group acts by just permuting the labels on the points. So the unordered configuration space of endpoints in the plane is also well understood. For example, so then the homology becomes a bit more complicated. The free part becomes much simpler, but there's a torsion part that's much more complicated. And if I recall correctly, this was first computed by Fred Cohen in his PhD thesis. So this is maybe the 1970s.
Matt, a question. Is it correct to say that physicists care about both the ordered and unordered, but maybe a little bit more about the unordered?
I think that might be fair to say. I think it would be better to ask a physicist. And in some ways, my limited understanding, not being a physicist myself, is that unordered might be a little bit more natural from the point of view of physics, in the sense that you really can't tell the difference between one particle and another. That particle, electrons don't really come with labels on them. The only properties, for example, an electron have are sort of its location in space, its charge, and so on. You can just list them, and it's important in physics, and especially in, say, quantum physics, that those are the only properties that the particle has. These are the observables, and so on. So, right. So that's a fair question. So here's an example of a point in our configuration space. So this is one point. So in this case, if there's 6 squares, that's a 12-dimensional configuration space, because we have to record 2 coordinates for each square. So there's some big complicated 12-dimensional shape that records all possible positions. And this is just one point in that space. And as the particles move around, you explore the whole space. Here's an old picture of the 15 puzzle. Let me just say something about who Sam Lloyd is, because I think he is kind of an interesting character. He was definitely a puzzle creator, an inventor, and he was also, I think, a bit of a con man or a hustler, and maybe a bit of a liar. So, for example, he claimed to have invented the 15 puzzle, but I think history is not kind to that claim. That it was invented. The 15 puzzle was actually invented by some postman much earlier in the 19th century. But Sam Lloyd did manage to sell a lot of these puzzles. And one of the ways he sold these puzzles was by challenging people to switch the 14 and the 15. If you look closely at the image there, the 14 and 15 are switched. And this poor farmer, whoever this character is losing his mind trying to, switch them back. So Sam Lloyd offered, this is like late 19th century, early 20th century, $1,000 prize. You buy the puzzle. He's like, if you can find some sequence of moves that switches the 14 and 15, then I'll give you $1,000. But that's 20th, or that's like year 1900, $1,000. So I don't know what that is in today's money. Let's say $1 trillion. It was a lot of money, and but I think he was confident that it was impossible. I'm not sure why he was so confident that it was impossible, but it was certainly proved in a math paper by Johnson and Story by 1879. So it was well understood that you can't just switch the 14 and 15. And it's a fun problem to give combinatoric students to prove this or to discuss in class together, some kind of parity issue. But I just want to point out that even this may be the oldest interesting mathematical fact that's known about the 15 puzzle. It's a statement about topology of configuration spaces of squares, because that, to me, that observation that you can't switch the 14 and 15, if you refine it just a little bit, or if you look at it more closely, what you're really saying is that the configuration space has exactly 2 connected components. I mean, saying that you can't switch the 14 and 15, maybe it's just saying that the configuration space is disconnected. But what I'd say is it's actually, I think Johnson and Story probably understood that that's sort of the only thing you can't do. So there's really only 2 connected components. So it's really this old fact about the 15 puzzle is already a topological observation. So what are the Betti numbers for just the 15 puzzle? So this is the case n equals 15, p equals q equals 4. Well, I think it's well known that the 0th Betti number that there is 2, that there's 2 connected components. But what about, is there any higher homology? Well, the kind of thing that we can prove with the methods in this first paper on hard squares is, Betti 1 is exactly this huge number that's roughly 10 to the 13, and there's no higher homology above Betti 1. So I'll say a little bit more about this later, but what one of our tools is to give a cell complex model for the configuration space of hard squares. So there's some cubical complex that we can deformation retract it onto. And so then the configuration space of 15 squares and a 4x4 square, that it turns out that in that case, the cubical complex that a deformation retracts onto is only 1-dimensional. So there's definitely no homology above dimension 1. And then we can just use the 1-dimensional Euler formula, V minus E equals Betti 0 minus Betti 1. And we can count how many vertices there are and how many edges. And we know Betti 0 is 2. And so then that last thing in that equation is Betti 1. So, this is just a simple computation once you have this cell complex model. Maybe this was already known what Betti 1 was for the 15 puzzle, but we haven't seen it in the literature. So that even that fact may be new. Okay, so let's talk. I want to show you a picture of what our main results are in this first paper on homology. The main question that we asked in this paper is just, when is homology trivial and when is it non-trivial? And we haven't completely answered that question, to be honest, but we've made some headway that I want to tell you about. So first, I'm going to show you a picture that summarizes our results, and then I'll state some theorems and just kind of like hint at the ideas of the proofs. So part of the reason I think it's hard is, we want to consider the jth homology for the configuration space of n squares in a p by q rectangle. So there's 4 parameters now, j, n, p, q. So to me, a complete answer would be necessary and sufficient conditions on that 4 tuple n, j, p, q, so that the jth homology of c, n, p, q is trivial, non-trivial. So we don't quite do that. But one thing that we found helpful, it's a 4-dimensional parameter space. So that's a little bit hard to picture. Let's picture a 2-parameter space instead. So what we're going to consider is area normalized coordinates, x, y, which we're always going to define throughout the talk in the following way. X equals n over pq. So that's the number of squares divided by the area of the rectangle. So in other words, that's the area fraction that the squares take up. Now, that is an interesting parameter from the point of view of physics, by the way, that's one of the parameters they consider. It's sort of related to the pressure of the system, right? Maybe, if you believe that it was behaving like an ideal gas, which I don't think is probably the right model, but, then pressure is inversely proportional to volume or something. So, this is the volume fraction. So n over pq is a very natural parameter to study. And then we'll do j, but rescale it the same way for the y coordinate. So we have n over pq for the x coordinate and j over pq for the y coordinate. And now we'll ask, when can homology be trivial or non-trivial in the xy plane? So that's a simpler, maybe slightly simpler question than in the npqj space. So this is the question that we're interested in, is when is homology non-trivial? So we have 2 kinds of flavors of results in this paper. One is homology is when homology can be trivial and when can it be non-trivial. So we showed that if homology is trivial, if homology is non-trivial, it has to be inside this trapezoid. All the non-trivial homology is inside that trapezoid. In other words, if you're outside of that, what we're really showing is if you're outside that trapezoid, then homology is trivial. what we think is probably true, so that trapezoid is cut out by 3 inequalities. Y is less than or equal to 1 minus x, y is less than or equal to x, and y is less than or equal to 1/3. We think that can be improved a bit. We think that, first of all, y is less than or equal to 1/3 can be improved to y is less than or equal to 1/4. And my favorite conjecture here, and something that I think is very fun to think about, is maybe y is less than or equal to x can be improved a little bit to y is less than or equal to x minus 8/9 x squared. So you see this parabola here. And so there's this smaller trapezoid, this blue shape is almost a trapezoid, but the top left corner of it gets cut off by this parabola. And the shape of that parabola is y equals x minus 8/9 x squared. We suspect that there's nothing outside of that parabola. So I'm going to tell we don't have, honestly, we don't have so much evidence for this conjecture, but maybe a little bit of, heuristic evidence, or, I mean, the main thing is that everywhere inside that blue region, we know how to construct non-trivial homology. So that's like kind of a converse. We do. So our conjecture is that all the non-trivial homology is inside that blue region. What we can show is that for every point in the blue region, there is non-trivial homology. So I want to make that a little more precise in a minute. But for example, what that might mean is for any rational point, because x equals n over pq and y equals j over pq, and n, pq, and j are integers. So clearly we can only talk about rational points. Those are the only ones we're interested in. But what we show is for every rational point inside that blue region, there exist n, j, p, q, such that x equals n over pq, j equals p over j over pq, and homology hj of c and pq is non-trivial. So if I'm allowed to make nj pq as large as I want, I can hit that xy, that rational point xy, every point inside that blue region. In fact, as we'll see a little bit later, not only can we find non-trivial homology at that point, we can find tons of homology. It's growing very, very fast, super exponentially fast, as the parameters, as n grows, say. So that's not much evidence for the fact that there's no homology outside of the blue region, but all our tricks only work inside the blue region. So finally, the last thing I want to tell you about this picture is you see some dots there. And those dots are everything we computed for n less than or equal to 6. So for small enough n, the cell complex that I mentioned earlier is small enough that we can compute homology of it. Already by the time, n is a little bit bigger than 6, where we have many millions of cells, and it's hard to compute homology. But for n less than or equal to 6, we were able to compute for every p and q what is all the homology. And every dot in that picture is a non-trivial homology group that we found, rescaled into these area normalized coordinates. So for some njpq, we found a non-trivial homology, then we just, x equals n over pq, y equals j over pq, and we plot that point xy. So that's all the non-trivial homology we found. So we found quite a few non-trivial cycles. We find quite a few non-trivial homology groups, but they're all inside that blue region. So maybe that's a tiny bit of circumstantial evidence for our main conjecture. But that's only for n is less than or equal to 6. We're saying no matter how large n, j, p, q are, there's no non-trivial homology outside of that blue region. So,
sorry, Matt?
Yeah.
Why is there asymmetry between x and y?
Why is there a symmetry between x and y?
Why isn't there symmetry?
Because x is n over pq, where n is the number of particles, and y is j over pq, where we're looking at the jth homology group.
Okay.
So just because n and j are different parameters.
Matt,
Are there
I have
other
a
questions? Yeah,
Yes, I was going to ask a question. So for n equals 6 or less than or equal to 6, you see light blue dots on the horizontal axis, but then beyond that, there's sort of like this empty wedge, Is there an explanation for that? Like as n grows, you know, do the blue dots all need to be
Is that the empty wedge you're talking about, this region here? Why aren't there any dots in that region?
exactly.
Yeah, I think that's just an artifact of n less or equal to 6. At some point, I stared at this picture for a long time and tried to understand what are all these dots, and I think they're all on lines, and I think the lines correspond. I don't remember what the lines correspond to. Does that correspond to a fixed value of n, or does that correspond to also y over x is constant? So the PQs cancel. It's a fixed value of n over j. Somehow, I think just the fact that n is less or equal to 6 is the reason we don't get into that little wedge down there, and that if we make n bigger. But again, as I said, one of the results that I sort of like in our paper is that for every point in that blue region, we can find non-trivial homology. The only caveat is we have to be able to let nj be pq be large. They might be quite large, but like, especially, you know, if you make the denominator of your rational point, the denominators of the x and y coordinates huge, it seems like clearly you're going to need to make at least p and q huge, right? So so in some sense that's necessary to make nj pq. But it was a little bit of a surprise to me when we realized that we could actually hit every rational point inside that region. So there really is tons of non-trivial homology there, but we still can't quite prove that there's no non-trivial homology outside that region. One more time, what we can prove is that there's no non-trivial homology outside of this slightly bigger region, that trapezoid that's bounded by y less than or equal to 1 minus x, y less than or equal to x, and y less than or equal to 1/3. That all the non-trivial homology is definitely contained in that region. But there's a little gap between what we know and what we expect. Okay, so let me start to just give you a couple ideas of our proofs. So SK is this sequence of points. We consider this for k equals 1, 2, 3, and so on. So it turns out that k equals 1 is the sort of top right corner of that blue region. And then k equals 2 is the, so k equals 1 is, so this is S1, S2, and then S3, S4, S5. So by the way, I lied a little bit when I was saying that the region is cut out by one of the bounding things is y equals less than or equal to x minus 8/9 x squared. In fact, what we consider to be the feasible region is just very slightly smaller than that. Less, you know, there's less than a 1% difference, I think. It's actually not this side here isn't, we think maybe it's not a bounding parabola, but a piecewise linear approximation to the parabola. Even these smaller lines, these secant lines that are strictly inside the parabola, we can't even find any non-trivial homology outside of that very slightly smaller region. But these points are, we think they might be extreme points on the region of allowable homology. So let me show you what happens at these points, SK, why we think they're interesting. So I want to sketch a proof of this theorem. For every rational point XY in this blue region, and again, so let me, the blue region is actually defined as follows. You take all of these SKs as k goes from 1 to infinity, and then you also throw in 0, 0, and 1, 0, and now take the convex hull of all of that. So that's our feasible region, which we denote with a script R. Okay, so the theorem about non-trivial homology is that for every rational point in the feasible region, there exists NJPQ. So that x equals n over PQ, y equals j over PQ, and homology is non-trivial. So let's just do the extreme points, SK, first. So here's the picture, S1. So what am I actually illustrating here? We have 3 squares and a 2x2 grid, and they can just, it's like the 15 puzzle, but much smaller and simpler. It's the 3 puzzle in a 2x2 grid. So I can slide the squares around. I can slide this square down, then this one over, and this one up, and so on. And eventually they all get back to their original positions. So that's a map from the circle into the configuration space. And I claim that it gives a non-trivial one cycle. I'll say something about why it's non-trivial in a second. But so in this case, P equals Q equals 2, N equals 3, and I'm saying it's a non-trivial one cycle, right? So then in area normalized coordinates, X equals N over PQ, Y equals J over PQ. So this, we get the 0.75, 1/4. So now we do something a little bit trickier. You can rotate these two around each other, these two around each other, and these two around each other in the 2x2 squares. So that gives you kind of 3 dimensions. But now you can also slide these bigger 2x2 squares around at the same time. So instead of a 3-dimensional torus, this is actually a map from the 4-dimensional torus into this configuration space. And then if you just work out what the parameters are, this is what you get. The 3/8, 1/4, by the way, is the top left corner of the feasible region. So here's the next point in the sequence. So with 3 squares and a 3x3 grid, the obvious thing to do is rotate 2 around each other, and then the third one rotates around them. And this is a standard thing in the configuration space of points. Cycles like this generate the homology of the configuration space of points. Fred Cohen talked to me about it one time as saying, you know, you have an Earth moon going around each other, and then those are going around the sun, you know. So that's just what's happening in each of these 3x3 squares. That's a 2-dimensional torus. That's a 2-dimensional torus. And that's a 2-dimensional torus. But then our trick is this nesting that, you know, the 3x3 squares inside the 6x6 square themselves can move around. And that gives you 1 more dimension. So this is a 7 altogether. This is a 7-dimensional torus embedded in the configuration space. And we claim that that gives you actually a non-trivial 7-dimensional cycle. So in this way, we can get all the points SK. We can definitely get at least 1 non-trivial cycle for every K. So why are they non-trivial cycles though? This isn't too hard to see. If we have a map from the torus into the space and from the space to the torus, then such that the composition is the identity, or even just such that the composition is degree 1 map would be fine. Then you have an isomorphism on homology, but you've factored it through this intermediate space that's the configuration space. So there has to be some non-trivial homology living in that configuration space. Again, this is like very familiar. This is the kind of thing you could do in the configuration space of points in the plane. And a little more precise statement would be like these maps from toruses into your space, they generate all the homology, but maps from your space to the toruses, you can pull back classes from the torus and those generate cohomology. There's a very nice survey article by Dev Sinha that gives you generators for the homology of the configuration space of points and cohomology together with a pairing, so that you can actually just completely understand what is the, you know, homology and cohomology of the space. So it's also, we got all these points SK. It's also easy to get 0, 0, and 1, 0. So then we just have to interpolate between them. So maybe I'll just kind of very, very quickly wave my hands at this. If we have, we just have some point that's a rational linear combination of some of these points that are the extreme points in the convex hull. But Carthay-Dory's theorem says if it's a convex combination of some of those points, it's actually a convex combination of just 3 of those points because we're in the plane. So just pick 3 points and we have a rational linear combination of them, convex combination. That's our point R1, R2 that we're trying to hit. And so lambda 1, lambda 2, lambda 3 are rational points. U1, V1, U2, V2, and U3, V3 are all points that are either SK or 0, 0, or 1, 0. So then you write these as fractions of integers. And then because these are from the set S plus, we can write them as fractions of integers where we even know a little more about. And then we write down these giant integers that are so big that these are also integers. They might not be because R1 is rational and R2 is rational, but we've made R so big that it clears all the denominators. So these are integers, N and J, and then we find a non-trivial class in H, J, C, N, R, R. And the way we do it, it's not only that those were integers, but lambda 1b squared is an integer. So it's a lambda 1 fraction of these smaller squares. We do this move, the move corresponding to the point U1, V1. We do that a bunch of times, and that fraction of the squares, and lambda 2 b squared of the squares, we do whatever we did for the point U2, V2, and finally the same for U3, V3, and then we put it all together. So like interpolating between these points is just a matter of like making a huge square and dividing it into smaller squares and just doing what we already know how to do in each of the small squares and just getting things to balance out. So it's just a simple computation, and there's not really any new ideas and interpolating between them. Okay, so there is something different we have to do to prove homology vanishing. Notice that, so this is just purely in terms of J, P, Q, and N, the first statement. If J is bigger than PQ minus N or N or PQ over 3, then homology is trivial. Or the way we stated it before was an area normalized coordinate for non-trivial homology. We say if homology is non-trivial and we're an area normalized coordinate, then Y is in that gray trapezoid bounded by 1 minus X, X, and 1/3. So how do we do that? Well, so we define a cube complex, and then so the definition of this cube complex is just, first of all, look at the big cubical complex in R2n that's just 1p cross 1q to the nth power, and take all the cubical cells of that cube complex that are strictly inside the configuration space. Some of them might be partly in and partly out. We ignored those. We just want the ones that are completely inside. And it turns out that the configuration space deformation retracts onto that cubical complex. And it takes us several pages to show that. It's not just a straight line homotopy or something. There's steps to the retraction. But once we have a cubical complex, game on, right? Now we could, in principle, we could compute anything. So once we have this homotopy equivalence, so just the dimensions of the cells in that complex already gives us that if there's non-trivial homology, J is less than or equal to PQ minus N. In other words, Y is less than or equal to 1 minus X. So that gives us that line that's the right boundary of the trapezoid and of the feasible region. Then on that cell complex, we do discrete Morse theory, and this is the main technical contribution of the article, is describing a discrete gradient vector field and analyzing what are the critical cells of that and what are their dimensions. And it gives us both J is less than or equal to N and J is less than or equal to PQ over 3. Unfortunately, the discrete gradient vector field that we use doesn't give you J less than or equal to PQ over 4. And it doesn't give you J as, it does give you Y is less than or equal to X, but it doesn't give you Y is less than or equal to X minus 8/9 X squared. We just tried, and that this doesn't prove our conjecture, this discrete gradient vector field. So it may be that discrete Morse theory will still prove that conjecture, but more effort, a different discrete gradient vector field will be needed. Just passing comment is that the cell complex also allows us to do exact calculations for small NJPQ. I mentioned this before with the dots in the figure. So there's some tables in our paper. So this is the kind of paper, this is what happened for n equals 6. For n equals 6, we only have to, PQ equals 2, 3 is the smallest rectangle they fit in. But by the time P and Q are 6 and 6, you've got the configuration space of points. So if you make P and Q bigger than that, it doesn't change the homotopy type anymore. So for n equals 6, this is the complete story. So here's another point, a picture of how one might look at the Betti numbers for, again, it's hard to visualize because there's 4 parameters, but what if we fix like n equals 6 and J equals 2, and then let P and Q vary? And so what we see is like 3 distinct regions. We see trivial homology, this homology out here is isomorphic with the configuration space of points in the plane. And the most interesting part is in between. And there the homology can be huge. This is analogous to when we saw that, the first Betti number of the 15 puzzle is huge, 10 to the 13 or something. The Betti numbers in between trivial and being isomorphic to the configuration space of points in the plane can be quite large. And in another paper or two, we call that the homological liquid regime. Okay, so let me just quickly summarize our new results from our last paper, because I know I'm out of time and we want to allow a little time for discussion at the end, questions and comments. So our new result that's on the archive is that inside that blue region, not only is homology non-trivial, but that it grows factorially fast. So what we mean is the following. From Stirling's formula, we see that log of n factorial over n log n tends to 1 as n goes to infinity. So it's growing like super exponentially fast, right? Like if you take the log of an exponential function, it's linear in n. Instead of getting something linear in n, we get something that's like n log n. So if we say that it has something has the factorial rate of growth rate of an factorial if log fn over n log n is approaching a as n goes to infinity. So what we show is the following. Suppose nj, pq are any sequence such that they're all going to infinity and n over pq approaches x and j over pq approaches y, and xy is in the interior of that blue region, the feasible region, then the dimension of the homology grows factorially with the number of particles, with n. But in contrast, if you looked at the configuration space of points, so we're looking at the configuration space of points, and we're in the regime where the degree of homology you're looking at is a constant times the number of points, then homology has the factorial rate of growth of j factorial rather than n factorial. And that's much smaller because we're only looking at j is up to, n over 4. So j factorial is much, much, much smaller than n factorial. So the homology is huge anywhere in the feasible region. So the idea is similar to what we did just to show non-trivial homology, but now we have to work a bit harder. The upper bound is easy, but we need a lower bound. And the idea is that now we're a little more careful. We don't just say we're composing a map from a torus and a map to a torus. We say, look, we have cycles from maps from toruses, and we have cocycles from maps to toruses that are pulling back. And we can't quite just look at those cycles and cocycles and do intersection theory, but there's a little trick where we can say, well, the cocycles, we don't quite look at the cocycle exactly, but that cocycle turns out to the fiber, the map to the torus has many connected components, and we pick one connected component and look at the cocycle there, that piece, and that it gives the right contribution to the intersection to the cap product, but then we can have a bunch of cycles and a bunch of cocycles indexed by the same set, and so that when they're indexed, a cycle and a cocycle, if they're indexed by different objects, that their intersection is trivial, and but if they're indexed by the same object, they intersect transversely in a point, and so then the pairing is 1, the cap product is 1, and so anyway, there's a computation to do. That one thing that I like about the way the paper is written now is that there's first a special case where we look at when the number of squares is exactly equal to, where the squares take up half the square, and the homology we're looking at is exactly 1/4 of the size of the square. And in that case, we can show that the Betti number is at least n factorial over 2 to the j. And this is this picture is important for that. But then it's a little more complicated argument to make all of that hand waving that I just did rigorous, and to prove the more general case, which again is n, j, p, q are all tending to infinity, but in area normalized coordinates, you're tending to a point. And in that case, then we can get some bounds on the Betti numbers. So let me just close with future directions. I would still really like us to show that if homology is non-trivial, then y is less than or equal to a quarter, or y is less than or equal to x minus 8/9 x squared. But so far, we don't know how to show that. So I'd be just as happy if any of you could show that, or maybe even better, show that that's not true. If you could find one non-trivial cycle outside of that parabola, y, where y is greater than x minus 8/9 x squared, then it's back to the drawing board, and all you need for that is just one example, one counterexample. So what we call in another paper, the homological liquid and homological gas regimes, is just, we say that you're in the homological gas regime if the inclusion of the configuration space of squares into the configuration space of points induces an isomorphism on homology. Because through the lens of that homology group, the particles are acting like points. So that's like the definition of an ideal gas, but from homology point of view. So what's known is if you have like a big grid and you delete 2 squares from it, so if pq minus n is at least 2, then it's connected, the configuration space. And in fact, that you get an isomorphism on H0, including the configuration space of points. So is it true that if you delete 6 squares, if pq minus n is at least 6, that you get an isomorphism on H1 and so on? It might be. So also, just one last thing, we talk about the factorial rate of growth, but that's sort of a coarse measure of how fast the Betti numbers are growing. As far as we know, it's the first real estimate of Betti numbers for any such configuration spaces. But we showed that the first order asymptotics is something like n log n, but is it possible that the second order asymptotics are like linear, and that there's some constant in front of the n, cxy, that's a function of x and y, wherever you are in the feasible region, and that everything else is smaller order. This would take some, it's possible that our methods could lead to something like this, but it would take a lot more work and more computation, and I think some more combinatorial insight. But anything like this would be really welcome refinements. So I'll stop there, and hopefully we still have a few minutes for discussion if anybody has questions or comments. Thanks, everyone.
Certainly, yes. So first, before we get to questions and comments, let's briefly unmute ourselves and applaud for the speaker. All right, so we'll start with public questions. So, but then after we stop the recording, maybe we'll have time for some private questions too if needed. But any questions for Matt?
I'd have a question. It's probably better to ask it at the end, but too bad I'm the first one. So you considered squares in a rectangle, right? How about cubes in a, what is it? 1 dimension higher?
Yeah, it's an excellent question. And that might be, even though physicists do study 2-dimensional systems like this, hard squares and hard disks, I think they find 3 dimensions to be the most interesting, because it kind of seems like we live more or less in a 3-dimensional, more or less Euclidean world or something. So I think we know very little. I don't even know for sure that our cubical complex model is a good, if there's a good analog of that for 3 dimensions. I suspect there is, that you could get a cubical complex that's homotopy equivalent to the configuration space of cubes moving around inside a cube, say, but we haven't done that calculation. And just doing it for the 2-dimensional squares ended up being a little bit harder than we wanted it to be. But I think that if I wanted to study the 3-dimensional version, that's probably where I would start, is seeing if we could come up with a cube complex model that captures the homotopy type of the configuration space. Because on one hand, if we can do that, then we can already do computations for small numbers of particles, presumably. On the other hand, if we can't even do that, then I worry about us being able to prove anything. But no, it's a very nice question.
All right, so
I might like it better. Yeah.
Let's go to David next. And I saw, David, you wrote in the chat as well, but please go ahead and unmute yourself.
Okay, thank you, Harry. I wanted to ask for the case when y is greater than 1 minus x, because from your work, you put for when y is less than 1 minus x. So what will be the case for y greater than 1 minus x? Would the homology be trivial or non-trivial?
So one of the things we show is that if y is greater than 1 minus x, homology has to be trivial. And that's, of these three theorems that I have on this slide, that one is the easiest to prove, because once we have the cell complex, it's immediate from the dimensions of the cells. So like, this one's kind of intuitive though. This one's the most intuitive to me, because so just to get a non-trivial one cycle, we have to delete one square, right? And then we can move 3 squares around through that empty square, kind of like the 15 puzzle. But if we have 2 squares that are missing, we could do that, you know, if the grid's big enough. If we have 2 squares missing, we could do that in 2 places, and that's a 2-dimensional torus. And if 3 squares are missing, then that's a 3-dimensional torus. What we're saying is you can't get 3-dimensional homology unless you delete at least 3 squares. You can't get k-dimensional homology unless you have at least k empty spaces in your region. So that's very believable, but the only proof that I know at the moment is through our proof through, once we have a homotopy equivalent cubical complex, and just looking at the dimensions of the cells in that cube complex, the dimensions of those cells are much smaller than the dimension of the configuration space. So already that's telling us something, that, you know, your homotopy type is smaller dimensional. I mean, this, by the way, this already happens with the configuration space of points in the plane. Like you have n points in the plane, so that's a 2n dimensional open manifold. So you might think there could be homology up to almost dimension 2n, but you don't have that. You only have non-trivial homology up to dimension n-1. It's more like close to the number of points rather than the dimension of the open manifold. And, you know, while you start thinking about why, and it's like, how can you make a cycle? Well, just think about making these toruses, like an moon going around an Earth and Earth moon going around the sun. And you start doing that, and you can make an n-1 dimensional torus. You can't make anything higher than that. At least you can't think of anything. So that's not a proof. But like one proof would be like, take the Salvetti complex, or take some cell complex that's homotopy equivalent to the configuration space of points, and just look at the dimensions of the cells. So this fact y less equal to 1 minus x is just comes from having a cell. That one proof at least is coming from the cell complex. I hope I answered your question.
Let's go now to Emmanuel, if you'd like to ask in the public portion, Emmanuel.
Hi, Emmanuel.
Yes, hi. Thank you for a very interesting talk, and actually your answer to the last question is a natural segue to my question. So, so you mentioned Salvetti complex, right? So for me, for where I come from is, of course, I naturally tend to think to these spaces as, you know, you don't have your arrangement of hyperplanes anymore, but you have some thickened version of
Absolutely, yeah.
And they are thickened in a kind of a boxy way, right? So, and what I was thinking is the usual way some arrangement people think about this is, you know, you can look at this a version of this arrangement in the real part of the complex space, right? That's the real arrangement of hyperplanes, and that's the main ingredient basically to build this Salvetti complex, which is a cell complex that has the homotopy type. Now, if I think of how this looks in the real, you know, in the real part, this is some kind of you can make a thickened arrangement, but you can make an affine arrangement of hyperplanes. And then I wonder, right? So my question is not really a question, it's just, I don't know, some kind of pre-associating. So my point is, maybe on a serious note, so maybe, you know, there is, you know, there are different Morse vector fields that are studied on the Salvetti complex. One of my, I mean, I have a list of questions actually. I mean, one of these questions was about minimality, which we know for complements of hyperplanes, right? Which means, you know, no torsion in homology. And one way you prove this, or one way you can prove this in them complexified cases, with some kind of optimal Morse vector fields. And the data for these Morse vector fields comes from the real picture. And, you know, I just wanted to put it out there. I mean, maybe you already tried this, but maybe looking at some kind of the cell complex that comes out from this construction. So look at the real part and do a Salvetti-like thing. I believe, I mean, I try to think about it live. I don't think it's very analog to your cube complex. And maybe even the dimension is different, and maybe that already tells you something. Anyway, that was just a comment. Maybe you have some comments on my comment, but very nice. Thank you.
No, this is all very interesting. Thank you for the comment, Emmanuel. So in an earlier paper, we studied configuration space of disks in a strip. And so you have an infinite strip and a plane and disks moving around. It turns out it's the same if there's disks or squares. And so it turns out to be a special case of this kind of configuration spaces that we study here, squares in a rectangle. Like if you fix the number of squares and you make the rectangle long enough, then it may as well be an infinite strip, that up to homotopy type. So in other words, configuration space of disks in a strip are a special case of these configuration spaces. And for those, one of our main tools was a different cell complex we use, and it turns out to be a subcomplex of the Salvetti complex. So again, we have to use, we have to prove the homotopy equivalence, and in that paper, it ends up being several pages, and again, it was more work than we wanted it to be, but it was one of our main tools was to get our hands on this cell complex, and then we can do computations. And we also do discrete Morse theory on that cell complex. And so then we started looking in the literature and saw people doing Morse theory on Salvetti complex and so on. But I don't think we know anything close to our discrete Morse functions are optimal or minimal or anything. And I don't think they are. We just get an upper bound on the Betti numbers from our discrete gradient vector field and a lower bound from these kinds of ideas where we give explicit cycles that look like toruses, and there's a gap. But in that paper, the gap is just a constant factor as the number of particles goes to infinity. So I think there's a lot to do here, and it would be really great if people who are experts on hyperplane arrangements or people who know a lot about Salvetti complexes and things like that, even just told us new cell complexes that might capture the homotopy type. I think that, I think there's a lot to do here. There's only a few papers in this area so far, and there's a lot we don't know. So, but another example is like disks in a box. That's what I started out interested in. Just disks. Let's say you have n disks of radius r and a unit square. We know that that's homotopy equivalent to a simplicial complex, but we don't have an explicit cell complex that we can do computations on. So, and the reasons why it must be homotopy equivalent are sort of like on the abstract side. We're just saying, oh, it's a semi-algebraic set, and every semi-algebraic set is homotopy equivalent to a CW complex or even to a simplicial complex. It's triangulable, but that's not very helpful. It'd be really nice to have Salvetti-like complexes or even subcomplexes of actual Salvetti complexes that capture the right homotopy type. But we only have that in a couple special cases, that disks in a strip. And then here we don't even have like a Salvetti-like complex for the hard squares case. We just have this cubical complex but that seemed like a natural thing to look at, something that lives inside the lattice for this case. Thanks again, Emmanuel.
Thank you for the answer.
All right, so why don't we end the public portion here? So thanks again, Matt, for a beautiful talk, and thanks everybody for all of your questions.
Thanks, everyone.